There isn't a huge clear distinction between sections 1.5 and 1.6 from College Board, but I tried my best to separate them, but there definitely will be overlap. So you can see in these two diagrams, we have the photon, and photons are made out of magnetic fields and electric fields. And so because they're made out of these two things, we call it electromagnetic, or EM, radiation. So we're going to be using the acronym EM radiation all the time. And so photons are energy. And so we usually correspond that with light, which we'll do a future lab with. So again, they're made out of EM. And so this photon moves at the speed of light, which is a constant c. And so this constant c is going to be moving and grooving. We know that this interacts with electrons. And so when photon, this red squiggle here, is hitting an electron represented by blue, the electron can move to a new energy level as seen in this diagram. And then when you have a photon leaving the electron, then that electron is not going to be excited anymore and it's going to go back to ground in this particular example. So there is two vocab terms we need when it comes to talking about waves. So we have frequency, which is the number of cycles per second, and we have wavelength, which is the measure from one point to the next point you go to the point. What I mean by that is that it doesn't need to be on the top of the peak like in these examples here, but you could start, for example, on this part of the peak, and then I keep going until I cycle to when it starts repeating again, and that would be the wavelength. So you can start again from like a peak or a random part of the wave, and eventually you can get that measurement. So again, frequency is the number of cycles that the wave goes through per second, and wavelength is the measurement between 2 points that repeat eventually. Okay, so we have EM radiation, and so the EM radiation goes through space as a wave, and again it is moving at the speed of light, which is constant c. And so we can use this information to get various things. So for example, we can get electron configuration using EM radiation in order to figure out that sample's stuff. And so here we have two diagrams, and these two diagrams show relationships between energy and frequency. And so what I want you to do right now is to take a few moments to look through these diagrams. And then I want you to answer the following. If you have a short wavelength, what happens to the frequency and what happens to the energy? And then if I have a long wavelength, what happens to the frequency and energy? So go ahead and just take a few moments to look this over, and then we'll talk about the answers in a few. Alrighty, ready? Here we go. So, short wavelengths. We can see short wavelengths over here on this part of the diagram. And so it corresponds to gamma rays being the shortest in this particular scale. And so I'm going to look back here, and so gamma rays are over here. And so you could see, based off the arrows up here, that short wavelengths have a high frequency and a high energy. So you can see those arrows pointing. As frequency increases, energy does too. And so I have my long wavelengths over here for radio and microwave, and you can see that they're long. And so looking over here, we have our long radio waves, and so long corresponds to low energy and low frequency. Make sure you know that relationship. We can visualize EM radiation using the Bohr model, as you can see here. And so as a reminder, the Bohr model is a very good model that we will use this year, but there are other atomic models that we will use for other purposes. You can see here when the electron is in ground state, and then we have a photon hitting it. And so when the photon hits it, the electron gets excited, as you can see here. When the electron releases or emits the photon, it can go back to ground, as you see here. And this phenomena we can actually see in a lab. When the electron emits a photon, we can physically see this with the color spectrum where the electron was excited and then went back down to a different energy level. you can measure the wavelength and frequency of this color too, which we will do in a future lab. We can quantify EM radiation using an equation. Now, remember, we are learning about theories. Everything that is established is a theory, including equations that we learn in this class. So in this case, this equation is the wave model theory, and it's for measuring waves. Make sure you can find this on the constant equation sheet, so you could see over here is a screenshot of it, and I have the equation right here. And then we have what everything means over here, whether it's a constant or whatever symbols there are or units. Now, obviously, you don't have to memorize it because you get to use the constant equation sheet, but you want to make sure that you know where it is, how to find it quickly, so that you aren't tripping about it during the test, because otherwise you'll be really confused and lost, and that wouldn't be great. So we're going to go ahead and go through each of the symbols and what they are. So first we have the speed of light. And the speed of light is a constant. And again, the constant is on the equation sheet, so you do not need to memorize it. Just make sure you could find it and then be able to know its units and stuff. Again, it is on the constant equation sheet. And then we have this symbol. This is lambda, and so lambda is represented by wavelength. Now we also, reminder, it is the distance between the two peaks. Now I like to use peaks, even though I mentioned earlier it can be any part of the wave, just because it's easier to remember, hey, just go through the two peaks. But again, you do it how you want to do it. And so frequency is represented by this. Now it looks like a V. It is not a V. It is the symbol nu, which is spelled N-U. So nu is frequency, and it is per second. Notice how I made per second with a superscript. So I will talk about that in a few moments. And so this is how many peaks are happening per second for a wave. And if you take future STEM classes, you will learn a unit called hertz, which is Hz, which is essentially just per second. And they just decided they don't like saying per second, so they just called it hertz. So that's just an FYI. Cool. And so what we use this equation for is if we have measurable stuff, then I can find out more information about a wave. I can also see how light bends and then do some experiments with that as well. And so looking again at the right part of the constant equation sheet, you could see that here we have the -1 symbol. So for the constants of this class, College Board likes to write it like this. I personally don't. I usually do slash, but I think they just didn't want to be confusing or whatever. So just make sure you remember that anything is -1 is per. So here, for example, the speed of light was ms -1, and so that means meters per second, so you could put m/s. So just keep that in mind. All right, so here is a quick your turn. And go ahead and try this out. Use the equation we just learned, and then you could see my little hint in highlighted right here. You could see that your answer should be around there. So go ahead and try this out, and then I will talk about the answer in a few moments. Already ready? Here we go. Okay, so you can see that we have our nanometers. Now notice that I have converted nanometers to meters because our constant C is given in meters. So I want to make sure units cancel. And so I used the original equation. I solved for nu because that's what frequency is. And then I made sure my units cancel. I made sure it made sense what the units I had at the end. And then I did estimation rather than using a calculator, so I'm not doing sig figs for this particular answer. But you could see that, doing it in my head, I got that answer. And again, it's per second. Again, the best way of writing it is s -1. So there we go. Cool. Okay. So we have the other theory equation. And this other theory equation is Planck's particle equation. So again, it's on the constant equation sheet up here, and then we have the various symbols over here. Now, I noticed that E just says energy. I want to make it very clear this is the energy of the photon for this class because we do talk about different kinds of energy. So we're going to focus on energy of photons for this equation. Okay. And so again, nu is frequency and h is Planck's constant. And so you can see Planck's constant again is right here. So make sure you could just find it and be able to use it. And then uses. So we can use the different, or this particular equation rather, to know how energy is used to move electrons around, and we can use the wavelength from the previous equation in order to correlate the energy to wavelength. And so knowing the energy of photons, we can again solve for different parts of it depending on what our, givens versus unknown in an equation are. And so when matter or atoms are, absorbing or emitting light energy, we could see those electrons move and then we can analyze that from there. And so one of the biggest things that we can use with this equation and tangent with the other one is we could do line emission spectra of elements, which is again something we will do in a future lab. So here's another your turn. So go ahead and practice doing this. We're using the previous example, so make sure that you can. And then also pay attention to your answer. So using the answer previously from the previous example, go ahead and try to calculate this out yourself. Pause the video and then try it out. Alrighty, ready? Here we go. So you can see we use the Planck's equation, and then we have the nu from earlier, which is here. And so literally I'm just taking Planck's constant, I'm putting nu, look, my units canceled, I'm left with joules, and then I got an answer at the end. So cool. Now notice that J is capitalized, so anytime you're talking about joules, make sure that you use J, capitalized. Cool. All right, now you could combine these equations if you want to, but you don't need to. But it is a handy skill to have, so I'll show you how now. So we can combine these two equations where we have certain constants. So here we had one of the equations, and then I did math to separate nu. And then we substitute nu into Planck's constant, and then we're going to have our combined equation here. So nice and easy. Again, you don't have to do this. You could do the math in multiple steps and then substitute and solve. Again, it really just depends on the problem. Now, there is a fun fact, right? And it's an interesting one, in my opinion. And the way that it works, because it's a fun fact, if you take Einstein's equation, so we know Einstein's equation, it's a famous one, right? And it's really cool, but I'm not going to go over like the whole thing because it's not part of AVChem. But essentially, if you take like this information, you use Einstein's equation, you do some mathy stuff, you can eventually prove that literally anything with mass and movement has a wavelength. Okay. Now, if you're like, what the heck does that even mean, right? You're proving that everything is particles and waves. Not just electrons, not just photons, like everything is a particle and a wave. So technically you are part wave and part particle too. And it's just nutty to me to think about that because it's just so bizarre. Okay, well, that's a fun fact. Anyway, when you're thinking about equations without math, here are two quick little problems. So looking at the formulas and then thinking about what we learned previously, and maybe this diagram as well, I want you to think about these two things. So pause the video and try it out yourself before I talk about it. All right, ready? Here we go. Okay, so the first question is a trick question because red or blue light, they're both light. So they both travel at the speed of light. It is a trick question and it's like, oh, dang. A lot of people get that wrong. And then which has more energy, red or blue light, we can see here. So we see blue light is around 470 or so. versus red light is at 700 nanometers. And so I didn't do the math, but I thought about the equation, right? Because I'm looking at the energy and I'm looking at nu and stuff. And so just thinking about it, since we have a higher frequency in the blue range, because again, this is, remember, the relationship between wavelength and frequency. And so because of that, blue. Yep. That's it. So there we go. Okay. So you might run into some other resources if you are going to learn this material from, other places. And they might talk about stuff that you straight up don't need to know for this class. So for example, quantum numbers. So you might run into quantum numbers with NLM and like assigning them and stuff. You do not need to know that. Same goes for Einstein. We don't really need to know that. We do need to know about photoelectric effect, but not like Einstein's math or anything. And then we don't really need to talk about energy quantized. This is from the old textbook, by the way, the page number. But like we don't need to do hardcore quantizing of the energy except what I just covered. There's also wave function stuff. If you take physics, then you're going to focus on that a little bit more. But the difference between chem and physics is actually pretty blurry. So that's why I'm pointing it out, because there is a lot of overlap because, physics uses chem, chem uses physics. That's how all science disciplines are. And then polyelectronic atoms, that is something you might run into, which you will not need to know. Okay, so we're going to be using inverse and direct proportional relationships in this class. So this is a quick review from either previous classes that you took or if you haven't learned it before at all. And this relationship that I have here is the abbreviated Coulomb's law from section 1.5. And so I'm going to use that to talk about inverse or direct real quick. And so a direct relationship is when one variable increases, then another variable increases, or the opposite, where one thingy decreases, then the other thingy decreases. An inverse relationship is when one variable increases and then the other variable decreases, and vice versa. If you don't quite understand this, I did include another video on my class website under Unit 1, so if you want to review that, go ahead. But one way that I personally use if I forget inverse or direct is by putting random numbers or in the variables. So you could see here in this example, I put a 5, a 7, and a 2 for these values, and I got a number, right? And so with that answer, I can, for example, see the relationship between Q1 and R. And so I can change the value of Q1 to something higher, let's say, and it's like this 11 over here. And I can solve for R doing, basic math. And then solving for R based off whatever answer R is, I can see, is it a direct relationship or an inverse one? Because again, if it's direct, they both increase. If it's inverse, well, I increased Q1, that means R decreased. So that's one way to know if it's inverse or direct, is just literally plugging in values. But there's a pattern to it that you can eventually notice, so you don't have to actually memorize that. But again, if you're in a pinch, it does help a lot. Photoelectron spectroscopy, also known as PES. I say PES, but I don't think that many people say it. But PES is an experiment you need to know based off how it works and what for. If you have a sample, you can pretty much find out various things. So some of the various things we can find are these things. And so IE is ionization energy. Again, we have electron configuration and so on. So what happens in this diagram? We have a high energy radiation, which is either X-rays or UV photons, and it hits a sample. So you can see the sample right here. This makes the sample eject an electron. So boom, it is ejected from the atom, whatever atom it happens to be ejecting from. The radiation used has a specific energy. And so whatever that energy is, we pick one, essentially, because you want to make sure that you know which electron you are trying to ding off. And so you want to be careful about that. And then when electron is rejected, or ejected rather, they are collected. So you can see that the electron here gets collected into this apparatus over here. And so when they are collected, it gets analyzed and it shows you some kind of data like this. I'm going to talk about this data on another slide in a few moments. Okay. And so, since electrons can exist in different energy levels, as I showed previously with the excited versus not, then we can see these electrons, right? And so since electrons can exist in different energy levels, you need different amounts of energy to analyze these electrons. And so some electrons will be more difficult to remove, aka more difficult to eject for this purposes of this equipment. And when, the electrons are really close to the nucleus of an atom, it's really difficult to remove those electrons. But why, though? Think about it for a second before I talk about it. Okay. Did you think about it? Did you try? Okay, so the reason why electrons that are close to the nucleus are harder to eject is because attraction. Remember, the nucleus has protons, and then electrons are negative, protons are positive, so they're attracted to each other, since opposites attract. If they are close together, then it will be more difficult to remove those electrons. Yeah. Now, we can also use paths to remove electrons from multiple atoms, so just keep that in mind. Cool. Okay. So, what is even being measured? So, we again decide how much energy our sample is getting. So, we input that energy. You could see it here. We inputted this amount of energy onto this sample. You could see this sample lost an electron here. And so this electron is moving, because this is kinetic energy, using that amount of energy. Now, it's not always the same, and that's okay. So, any extra energy, so for example, there's a certain amount just to make the electron move off the atom, then the extra energy is how fast that electron is going to move. So because that electron is moving at a certain amount, again, that is the extra energy. And so in this example right here, we have a small amount of energy used to remove that electron from the sample. And we have lots of energy left over. That means the electron is moving super duper fast. It has a lot of kinetic energy. And so if it took a lot of energy to remove the electron from a sample, then you wouldn't have as much energy left over, and the electron is going to move really, really slowly. So you want to keep that in mind when you're analyzing the equipment, if there's a question about that kind of stuff. All right, so here is an example graph that you can get from PES. And so let's analyze what is even on this graph, okay? So reading the graph, we have axes. So notice we have relative number of electrons. So again, the relative. So we're going based off estimations and stuff. Then we have the energy over here. This is the energy that we can measure. And so the height of these peaks here, we can count how many electrons are equal to that energy to eject. So this energy is how much is used to remove that electron from a sample. And these electrons are at specific energy levels, right? So think about the Bohr model again, how the electrons are being moved. And so essentially we're just straight up removing it from the atom. And so this x-axis, again, is the energy required to remove those electrons. Make sure you know that, because students forget that sometimes. Cool. All right, so here is an example. So this is hydrogen. If I look back on my periodic table, hydrogen has one electron usually when it's stable. And so you could see I have one peak and it corresponds to one electron. That makes sense. Okay, so we have helium as our next example. And so you can see that we have one peak on helium. And as a reminder, when helium is neutral, it would be 1s2 for its electron configuration. And if you notice, there's 2 electrons. Ooh, coincidence? No. So there is absolutely no coincidence. Because if we keep going with the pattern, lithium, we know lithium's electron configuration is 1s2, 2s1, and if I notice, the first peak corresponds to 1s2 because there's 2 electrons here, and then this peak over here, you notice that there's only 1, and that corresponds to 2s1. So that makes perfect sense. I keep going. Beryllium. Beryllium is 1s2, 2s2. Notice this peak is 1s2. This peak is 2s2. So I can continually count across and I can find the electron configuration of this substance, and then therefore I can find out what this substance is from looking at the graph. And so I can keep going with some examples. So boron here, I have 1s2, 2s2, and then 2p1. So if I just keep on going after that, here is a bigger example, and I'm going to go ahead and show the whole thing. And so if I go through this whole thing for scandium, this is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d2. Now notice this is weird, okay? When you look at the orbitals, they're really close. So that's why you might not have the perfect analogy of going across and getting the electron configuration. But as long as you know how to count stuff, you should be fine. And it makes sense. So I haven't seen that many complicated PES graphs on the AP test, but you just want to keep that in mind when you're looking at these graphs, that you might have some weird anomalies like this. Cool. Okay, so try this your turn, or think about it actually. So why does boron need more energy to remove electrons compared to beryllium? Because remember, this x-axis is talking about the amount of energy involved. So you could see here boron is 19.3 versus beryllium is 11.5, and you could see here and here there's more. So think about it first. Your hint is electron configuration. So think about it, and then I'll talk about it. Okay, ready? So the reason why is suborbital p electron. Woo! That's the main reason why. There's also the fact that boron has more protons, and when you have more protons attracted to the electrons, you have Coulomb's law all over again. So just make sure you know how to explain with Coulomb's law properly. Yeah, cool. All right, we have a second your turn. Here is a chart. Can you figure out what the electron configuration and therefore what is the element of this chart? So go ahead and try it out first, and then I'll talk about it in a few moments. Ready, ready, ready? Okay, here's our electron configuration. 1s2, 2s2, 2p6, 3s2, 3p3. And then if I look at my periodic table to find the pattern for electron configuration, it is phosphorus. All right, so here are two graphs. And so you can tell that data isn't quite perfect. You can see that nothing is like particularly straight when you're talking about counting electrons and whatnot. So like this is a chart that we've seen before. We can see that it has two samples, but this chart is black and white, so it looks the same, but whatever. And then you could see sometimes data is not quite perfect in real life compared to in person. So AP Chem, we're going to stick to nice and easy charts to read, but in real life, you have to keep in mind certain other things. Cool. That is it for this section. Good luck on understanding everything else. Okay, bye.